Hello everyone, welcome to my channel. So in this video, I will continue my introduction of probability. So in last video, we already talked about what is continuous random variable and how we can use the probability density function to describe its distribution. So in this video, I want to introduce one more method to describe a continuous random variable's distribution. This is a cumulative distribution function. So the definition of our cumulative distribution function looks like this. So if you assume x is a continuous random variable, then the cumulative distribution function of this random variable x is actually the probability of our capital X smaller or equal to small x. Okay, so in fact, if you look at our axiom of probability, what we will know from this definition. In fact, for our probability, for here, so then the first thing is in this definition, we know the value of our x. This is between our negative infinity and positive infinity, and also become for our axiom of probability, the probability of all possible value for our probability should equal 1. So in other words, if we say this is a probability of our capital X smaller or equal to infinity, that means this should include all of the possible values of our continuous random variable. So in other words, this means we take a limit of our x goes to infinity, positive infinity, and this one will equal 1, because that will make sure the probability of all of our possible value of our x is equal 1. And then similarly, because all the probability should be a non-negative, so that means we have the second property is for all of the value of our fx, this should greater or equal to 0. And then the third one is, for this one, what we will have is because all of the probability for each possible value should be a non-negative probability. So then what we will have is if we have A and is smaller or equal to B, then what we will have, we should have the cumulative distribution function at A should also smaller or equal to the value at B. So this is a third requirement or property. And the last one of this one is also by the axiom of our probability. So if we say the probability of an empty set, the value of this should always equal 0. So that means if we say the probability of x is smaller than negative infinity, because x is always larger than negative infinity, so this one actually is an empty set. So we can denote this by x goes to negative infinity of our limited for our CDF, and this one should equal 0. Okay, so this is a four important property of our cumulative distribution function. So then in our last lecture, we already talked about the probability dense function, and I said in the beginning of this video, I said these are two methods to describe a distribution of our continuous random variable. Then maybe you will have a question, what's the relationship between this, or what's the difference between this? So here, let me give you the relationship between them. So if you assume a probability density function of a continuous random variable x is denoted by a small f, and the cumulative distribution function is denoted by capital F, then when we have a PDF here, then we can use this calculus to help us compute the CDF function at any value x. And also in other direction, if we know the CDF of our continuous random variable x, then we can use the derivative to compute our PDF. So the only thing you need to care for is about the range. So for our CDF, the range, the domain for our CDF is between negative infinity and positive infinity. And then for the second one, because we want to take a derivative of our CDF, capital F, so, but if you are familiar with the calculus, you know there are some cases the derivative is non-exist. So if you are not familiar with this materials, maybe you can review some materials on when a derivative is exist, or maybe you can leave a comment under this video, and maybe I will upload one more video about calculus. So here, to compute our PDF, we can only compute this when this derivative exists. Okay, so this is a relationship between these two methods to describe a distribution of a continuous function. So now what I want to do is we look at one example. So what we have in this example, we have a defined PDF probability density function. This is actually a step function. So our value of this PDF depends on the value of our x. If x is smaller than 0, the value of our PDF is also equal to 0. If x is between 0 and 25, then the value of our x is equal 0.04. And then if x is larger than 25, then the value of our PDF is equal to 0 again. So the question is asked us, what is the CDF, the cumulative distribution function of this random variable? So here, to compute this one, what we will need, we will use the relationship between our PDF and CDF to compute it. So here, by this relationship, what we will do is we will take an integral of our PDF, probability density function. So this is equal to negative infinity to x and f. So here I change the letter inside our parentheses to u, because I want to differentiate this with the upper limit of our integral. Okay, so here, because our original question of original PDF is have a 3 branch. So what we will do is when we plug in the value to our integral, then of course this will also depend on the value of our x. So here, in fact, what we will have this is also equal several branch. So then also we change this to 3 branch. So what we will have for each of the branch. So if we look at the first one, the x is smaller than 0. So in this case, the value of our PDF is always equal 0 in this case. So that means here, what we will plug in this equation is we will have this is equal integral from negative infinity to x, and the value of our PDF is 0 du. And then when the x is between 0 and 25, what is the value of our PDF? Actually, there are 2 possible values of our PDF. One is when x is smaller than 0, the value of our PDF is 0, and when x is between these 2 parts, the value of our PDF will equal 0.04. So that means when we compute this integral, we need to divide this to 2 parts. One is from negative infinity to 0, and the other part is from 0 to our x. So when the interval is of our integral is between negative infinity to 0, the value of our PDF should equal 0. So that's why here we have this is 0 times du. However, for the second segment, in this case, our value of our PDF will equal 0.04. So that means here we should plug in 0.04 to substitute our FU here. So this is a case when x is between 0 and 24. And then the last case is when x is larger than 24. Then what we will have for our PDF, we will have all possible branch, all possible values for our PDF. So what we need to do is now we need to divide this interval to 3 segments. The first one is still negative infinity to 0, and the second is from 0 to 25, and the last is from 25 to x. So in this case, for the first segment, is same with our previous branch of our CDF. This is still 0 times du. And then for the second one, if we look at our definition for PDF, we will know this equals 0.04 du. And then for the last one, because now for our PDF, it will go back to 0 after x is greater than 25. So that's why here is 0 times dx again. Okay, so now what's the final answer to our CDF? So what we should do is we should compute this 3 calculus for the 3 range for our x, and then the final answer will be look like this. So this is how we can compute our CDF. Okay, so this is the way we can compute this CDF, and then we can see like when actually if you compute this by yourself, you can use our 3 properties for our CDF to check this one. So the first thing is when x goes to negative infinity, the value of our CDF is equal 0, and then when x goes to positive infinity, the value of our CDF should equal 1. This also satisfied. And then is all the value of our CDF is a positive value, so the answer is yes. And then the last thing is if we choose any a and b between negative infinity to positive infinity, we can find for our fx, we will have this is f at a should smaller or equal to f at b. Okay, so in other words, our CDF generates a non-decreasing function. And here, if we want to draw a graph of our this CDF, so what we will have is assume this is our x-axis, and this is our value for function CDF. Then we will have this is a 0, and here assume this is a 25, and for our value is for y-axis is 0, 1. Then the graph of our CDF should look like when it's smaller than 0, it's just equal, when x smaller than 0, the function is equal 0. When x is larger than 25, the function value is equal 1. And then when the value is between 0 and 25, this should be a increasing line, looks like this. Okay, so this is what we have for this CDF, and you can see this is a non-decreasing function here. Okay, so that is my explanation of the CDF of a continuous random variable. So please subscribe my channel. In next video, I will start talk about what is the mean, how to compute the mean and variance of a continuous random variable. So hopefully I will see you in my next video.